So we need a solution like we need a source for gravity. The source for gravity technically what you are called energy movement tensor, which you are taking something called ideal flow. That means you can model the form of the fluid. So you can apply fluid dynamics, they can model the entire universe. So it gives different kinds of the solution to the universe. So this depends upon the what is the dominant form of the energy source within the universe. Suppose the universe dominates the matter, then the dynamics of the universe is governed by matter. Or the universe is completely governed by the radiation or dominant form of the radiation. Radiation will be governed the dynamics of the universe. So vacuum, which is under whatever dark energy is the correct level. So which is the dominant form of the given course of time, that will determine the dynamics of the universe, evolution of the universe. So it's very interesting one can find something called the scale factor of the universe, which is some sense you have described the geometry, which can connect the time evolution, and the temperature time also can be connected. So we see go back in time, then we reach a point where the density can be infinite, the temperature can be infinite, and in this scenario what we are calling so-called Big Bang. So this is can be taken as something where we know the universe, or we can describe after a few moments of the universe, one can describe up to today. So this is the success of the standard model cosmology, which is based on the Einstein general relativity. That's the power of the Einstein relativity. So then the standard model cosmology is successful to describe many phenomena, but it is failed to describe something like a horizon problem or a homogeneous problem. So why the observed universe look like a flat? Or why there is something like cosmic microbial radiation coming from different parts of the universe is we are on the same temperature. So standard cosmology could not answer one. So to address some of the problems standard cosmology, an idea could introduce later. This idea was introduced much before, but it was not popular among the cosmologists. This idea became familiar only in 1981. A postdoc from the MIT, he introduced an idea, and that was known the inflation. So according to inflation, the universe had an accident phase, a very early stage of the universe. So it could explain the observed universe is look like a flat, and why it can be explained the formation of the galaxy, etc. So one of the so we have more than 100 modes of inflations available today, but we don't know which is the correct mode of inflation. So there is not just observation coming first to microbial radiation, comparing the various satellite observation like Planck satellite, other satellites one can model, pin down which is the correct model of inflation. So many modes are rolled out based on certain quantities which I will describe it later. Yes? Yes, they are observed limits. Can you come some observation? What is that scalar ratio? Yes, there is an upper bound. I show you what the upper bound that is there. So this roll parameter can be connected to something called a tensor scalar ratio. It is direct rate of something called first order parameter. It can be estimated from the observation. Okay, so this is the dynamics of the universe can be described in terms of the inflation. So called inflation field. So inflation field is the one we are using it, and the corresponding action. From this action one can get some sort of equation of motion. So then this is the Einstein field equation, called the Feynman's equation. So there is a condition, then only the inflation will happen actually. So this is something like kinetic energy of the inflationary field, and it's called potential energy. Whenever the potential energy is very high energy only, compared to kinetic energy, inflation can happen. So this condition, what we are calling a slow roll condition. Under that condition only inflation can happen. So which means that the potential can be considered a metastable vacuum. We know that system will not be a stable configuration. It is a metastable state. It has to come to true vacuum or minimum. So the time at which that is what's called the duration of the inflation. So under application of this condition, Einstein Feynman's equation can be reduced to this form. So this usually can be characterized through parameter called slow roll So in order to trigger the thermonuclear reaction, we need a certain kind of temperature that they could not achieve. So they achieved only something called a particle creation happened in this stage, and the created particles were moving randomly, collide each other, and that collision raised the temperature of the universe. Then we could reach the reheating stage of the universe. Then we could achieve the thermonuclear synthesis of required temperature, then subsequent is can be described the standard model cosmology. And then another problem with this model is called a cold inflation, because the universe expanded, the temperature went down. That's called cold inflation. But here's another issue. There is something called quantum classical transition, which cannot be described with this cold inflation model. And this model which I described only in the classical model of the field. And we know that the classical any model or the field which has a classical pattern, zero open oscillation or quantum fluctuations. So quantum fluctuation is ignored here, what I mean, but actually quantum fluctuation must be taken into consideration. This quantum fluctuation will ultimately see to the formation of the large spectral threshold in that video. So therefore the field can split into classical part, a homogeneous part, and a quantum fluctuation part. The quantum fluctuation part only can get computed. So you can root the mean square fluctuation is can calculate. That's what we are calling a power spectrum. So which is the quantity which can compute from the inflation as a initial power spectrum. So this power spectrum can be connected to observations. So there are two types of perturbation happen. One is called a scalar perturbation, which is the formula of the galaxy 17. So there is a perturbation of the, because these are source for gravity. Once you perturb the source, it will automatically perturb the geometry also. The geometric perturbation is something called the gravitational waves. So it is the origin of the gravitational wave. This is not the gravitation what we are getting from the conventional literature. So this gravitation is called primordial gravitation, which is originated from the early university. We are not detecting this one. So this is very sure that if you take this one, you will get a Nobel Prize. So the gravitational generation also requires the inflation. So if you are detecting gravitation, it is an indirect way of testing whether influence will happen in the universe or not. So the main drawbacks of this inflation model, I mentioned that we cannot describe it, and it will require an additional mechanism to reheat the universe. So this problem can be overcome with something called a warm inflation. Now I answer what the friends are asking. So this is the tensor to scalar ratio, which is connected to the first order parameter, 60 times epsilon. So this R can be estimated from the observation. Right, therefore you can always understand what the potential of the inflation. So you can read back, calculate it, going back, then you can determine what the energy scale of the inflation, what happened actually. So to overcome this model and another model called warm inflation, people introduced later. This is something long time back we used warm inflation. The main difference between the cold inflation and warm inflation is, so there is a particle creation during the inflation itself. Where the cold inflation, the particles happen at the end of the inflation. And then there is a radiation baths available here. It is something like you are putting harmonic oscillator in a thermal bath, so that's the basic model you can do it. So there is a particle creation continues happening here. But when the particle creation happening here, this field has to interact with other fields. Where the conventional cold inflation, there is only one field was responsible for the entire inflation. So here still inflation is only to the something called infraton field. It's a part of the time element or homogeneous scalar field. But compared to cold inflation, this field also interact with other fields. So conventional inflation, we have only one field, there are no other fields. Other fields were created in the later part of the universe only. Whereas this case, along with them, other fields also could exist. Therefore, they could interact during the inflation. The particle happened during the inflation. That there is something called the dissipation happen. So this dissipation mechanism creates a thermal bath during the inflation itself. Therefore, you don't want additional mechanism to reheat the universe. Therefore, completely different. Then same time the stored parameter can also get affected. So stored parameter can get modified. Therefore, the equation motion will get modified. I tell you. So this Lagrangian is only for the solid response for the inflation, and this is only scalar field. And we can see that other fields available. Other fields in general as well as X and Y. Some of them could be bosonic field, some of them will be fermionic field. Other one is normal scalar field. And it's a 7 field can be represented. 7 X are there, 7 Y's are there. There are multi fields can be represented to X and Y. Some of them could be fermion, some of them will be boson. Because supersymmetry we consider corresponding each system with all percentage. Supersymmetry comes in the later. Now we can see some equation portion be modified. See, here this is basically from our original old information, and the Q, which is connected to special parameter. This is the modified equation of motion. Similarly, you can see that the throttle parameter also gets modified because of the thermal bar. So these are here our old information we had only quantum fluctuation, but here we have thermal fluctuation also there. Then the question is which is the more dominant over the other one. So you can see that here are two kind of averaging. Earlier to compute the power spectrum, we have to compute only quantum fluctuation, root 2 means fluctuation was sufficient. But here you also have a thermal fluctuation. So there are two averages should be there actually. One is over the quantum averaging and the other one is the thermal averaging. So thermal averaging more dominant than the quantum averaging. Therefore, this is the quantity you get it. So thermal fluctuation. Yes, all things will come. So that is the main problem for the some model of this one. I am going to explain that one. Yes, you are right. So the thermal fluctuation is a hard dominant over the quantum fluctuation. Now, based on that one, there are different types of models of warm inflation. So basically, I mentioned that the scalar field, which is more poles of the inflation, can interact with other field, which was not there in the old inflation quantas, where that's possible the warm inflation quantas. Therefore, depends on what interaction is possible, that can lead to different types of warm inflation models. So I will discuss you there are four types of inflation model, warm inflation models. So quickly, then it will come to some conclusion and then justify the type. Okay, one is called the distributed mass model. So this is basically originated from string theory model. We know that string theory is the most fundamental theory. Somebody asked me one question, is there a theory for everything? Some says superstring theory can be theory for everything. That we can have a separate discussion not now. But so the string theory advantage is that string theory has something called a multiple vacuum. There is something called a string landscape for a vacuum. Each vacuum means corresponding existence of field. So the fundamentally how the particles are fields are can originate from the string itself. We can explain that one. So each vacuum corresponds to each field. That means the existence string theory itself has the existence of multi-field. Therefore, the warm inflation is naturally each have different field required for different interaction. So nature multiple fields are very natural like a string theory. Therefore, there is no problem. The cold inflation, we compute cold inflation model, the inflation field can interact with many fields. That's what the Lagrange may have showed. That Salisa was asking the same question, why you have X and Y. X and Y basically originate from string vacuum. There is a possibility of multi-fields. But the main problem is that the field has the different vacuum. So field can interact n number of fields. So when you interact n number of fields, there is something called the thermal mass can increase. See, there you have only, that is unique vacuum we can get only flat space only. The moment you are talking the curves, so there is nothing like unique vacuum. Because you can compute through bubble coefficients can gather into vacuum which are related to each other. The unique vacuum which is Lorentz invariant possible only provide the entire space time to be flat, Euclidean. Yes, but if you are dealing with the curved space time, there is nothing like unique vacuum. But different vacuum can be connected in bubble transformation. They can compute with the radiation particle. That's scalar field. What is scalar field? Is responsible for inflection. Inflection happening in scalar field only, based on change. But the difference is that it is also interact with other fields. Pi 4 coupling is possible, pi square coupling is possible. Otherwise, you will not get that dissipation. Dissipation required interaction. That will create the environment always in warm. Likely you need interaction. Temperature. All inflation and this one. All inflation is self-interaction there. That cannot generate. It can generate, but that the radiation density very, very small compared to the actual density of the inflation field. Because this quantum classical friends cannot explain. And it is called additional reheating mechanism. So I mean, at the cold inflation. So this can overcome because there is a particle creation happening during the inflation itself. Because it impacts other fields. And it will be thermal always. So you will have a radiation field along with the other field. Right? So you will get the thermal fluctuation here. You don't want additional reheating mechanism. Because it's alone cannot. It's alone cannot because it can only self-interaction. Self-interaction is not possible. It is possible, but it cannot create any kind of temperature. Temperature both ways, dissipation should happen. So that's called thermal bath. That's called thermal bath here. So that thermal bath can create. So it is something like other fields are the environmental field. So that other fields are the environmental field and the inflation field is the one driving the inflation. Right? So that it is something like your thermal bath extend the energy and heat and energy stream. The same kind of model is not possible. Other fields are not just a bath, environmental field and the inflation driving on the scalar field itself. But at the same time there will be interaction between. That interaction can create a temperature. That will make the field always warm in condition. So there is no need to additional reheating mechanism. So particle creation also happens at the same time. But the question is whether the system was in a thermal equilibrium or not, or what kind of mechanism. It was thermal equilibrium naturally. Therefore, you have to always compare the interaction rate with the expansion rate of the universe. The certain condition is satisfied. Yes. Yeah. Yes. Yes. Our field. The origin of the other field I will estimate. Because the moment you talk about string theory, naturally other field can also coexist with the inflation field. That's our plan. Okay. So what is quantity which can be computed and which can be connected to this dissipation coefficient. Dissipation coefficient you can see it depends on whether there is single field only. Dissipation gamma. So you can actually connect this one to various observations. Let me consider it as an observation. So the total parameter which is called the tensor scalar ratio. The tensor scalar is something called the power spectrum called the NS power spectrum scalar spectral index. So you can see that this is the quantity which is coming from the observations. So this turquoise blue which is giving the most 16% confidence interval, any line which is passing through that quantity can be more acceptable compared to observation. So corresponding to scalar ratio you can see the value of the Q which is something like a thermal coefficient kind of thing which is related to the dissipation coefficient. The value is very small here. So this is called a small dissipation coefficient, weak regime of the warm inflation. There are two regimes called a strong regime and a warm slow regime. So strong regime is Q value must be very high. This is a slow regime. So there is another model is here. I can also consider in terms of pi raised to 4 potential. Then one can compute it. So what you are getting is this is also some points are just outside the confidence interval. So this value is not, but there are certain values which are acceptable. You can see acceptable value from this range only. With these values, one can explain the current upper bound of the tensor scalar ratio. That's what 0 is coming from its observation. That means this model can explain the observed values without the whole inflation. That's advantage. So one more model which I call warm inflation, warm liquid inflation. So there is due to the phase transition case, there are two types of field can generate here. So this field, there are minimum number of fields only required for interaction. So here you can see that this warm inflation, liquid inflation, because the field which can take a small mass. So here there will not get additional thermal mass, not will not generate it. that will not arise any kind of the renormalized sphere. So here you can say that there is only minimum fields only ingredient sufficient to describe this model. Therefore, this model is called the minimal warm inflation. The four models you can see that. So this model also will compare various observations. You can see that this comes to strong regime because the Q value is much higher than the Y one. So we have models which are strong regime and weak regime. Some values can be explained, but in general you can see that the warm inflation is more acceptable than the cold inflation because of the more realistic look than the cold inflation model. Now I skip this one. As an application of this one into something called modern issues called different Hubble parameter which is obtained from various observations. So this is what is called Hubble tension. There are two prominent set of values. One is coming from the Planck data, other one is the Schultz data. Schultz data basically local measurements of Hubble parameter, and Hubble value is coming from the CMB called the large cosmological parameter value. So you can see that the CMB data around maybe 68 the value, where the Schultz data gave 73 in terms of units. So there is a lot of the difference between the Hubble parameter coming from the, we are measuring the same universe, we are supposed to say what the rate of expansion of the universe. This is estimated telling the Hubble parameter. Why one observation is one value, why other observation is other value. This is called Hubble tension. Can we resolve this issue? What is the main problem to resolve that one? So earlier we have worked out this problem to using something called quantum gravity. So what we have suggested that if you apply quantum gravity effect, which is originally neglected during the inflation, the original setup, what we have shown that the quantum gravity will affect during the inflation, it can resolve the, or it can interpret the Planck data and the Schultz data so that we can resolve it.
So your times, so
5 minutes will take the time. So I take 5 minutes. So now what we are showing that warm inflation, which is basically multi-fields. The multi-fields are basically coming from the string theory point of view. String theory is a normal string theory, a super string theory. Super string is the theorem of quantum gravity. Therefore, what we are showing that using this warm inflation model, which is basically regarded as super string theory, it's a theory of quantum theory of gravity. So without quantum theory of gravity, we cannot discuss about the existence of the warm inflation itself. Otherwise, the original warm inflation is basically rooted from the quantum gravity perspective, which is version from the quantum gravity point of view. This warm inflation sometimes is a reflection of the quantum theory of gravity. So you can see that that's true. To be able to explain warm inflation can also explain the Hubble's data observation. That's what we are showing here. So you can see that the Schultz data which can be explained. Now compared to earlier one, that also comes from the quantum theory of gravity, and this warm inflation can also explain the Hubble's data, which means that this also can be explained from quantum theory perspective. So therefore, what I am concluding that warm inflation is capable of interpreting the, or can resolve the Hubble tension. So therefore, to resolve Hubble tension, we need a quantum theory of gravity. Quantum gravity effects must be there. We are very difficult to see quantum theory of gravity, but that does not prevent us to test the quantum gravity observationally. The inflation related observations are basically effects of quantum gravity there. One can really assess the existence of quantum theory of gravity. Therefore, the existence of warm inflation, which can explain the Schultz data or the Hubble's data, which means that this is also related to quantum theory of gravity. Therefore, I am justifying the title that warm theory is a reflection of quantum theory of gravity. What is a quantum gravity effect?